Okay, electron configurations. This is all about where electrons are located in the atom. It's kind of a bookkeeping structure, right? A way to keep track. And there's actually a reason for it. It's going to allow us to refer back to certain electrons easily if you understand where they're located within the atom, right? So kind of the purpose is to give organization to the electrons in any given element, right? So the first idea is that in any atom, there are different energy levels. And if we recall the Bohr diagram that looked like this, it was like rings. The Bohr diagram said there's energy level 1, there's energy level 2, energy level 3, and so on, right? It went up to 7. So clearly from the Bohr diagram and just from common sense, you know that with each additional energy level, the newer energy levels are bigger than the previous. So energy level 3 is bigger than 2, 4 is bigger than 3, and so on. Okay? So to elaborate on that a little bit more, energy level 1 is the smallest energy level. Now every level is split up into what we call sub-levels, right? And in energy level 1, the only sublevel that's there is S. It's just a sublevel. We just designate it as S. In energy level 2, which is bigger than 1, this is going to have two sublevels. It's going to have an S, and it's going to have a new one, which we call P. So as we progress into bigger energy levels, we see that there are more sublevels. So first, are you guys okay with that? Right? The higher the energy level number, the more sublevels there are. I know this diagram doesn't show all of them. I mean, we could kind of continue to add to it, but as it turns out, there's not really a need for it, which I'll explain later. So, essentially, what we're saying is this. The energy level number equals how many sublevels are in that level. So in energy level 2, there are 2 sublevels. In energy level 3, there are 3 sublevels. In level 4, there's 4. In energy level 5, there's 5. In energy level 6, there's 6, and so on. Okay, so if I said how many sublevels are in energy level 8, how many are there? There are 8. And the first one is S. And the second one is P, and the third one is D, and the fourth one is F, and the fifth one is G, and the sixth one is H. Okay, it kind of goes on that way, right? All right. So if you're okay with the fact that in each energy level, the bigger it gets, the more sublevels there are. Now let's talk about what those sublevels actually look like. S sublevel is found in every energy level, right? And because we're talking about an atom's three-dimensional space, if we refer to an XYZ plane, S sublevels look like a sphere. This is 1S. This is the smallest sublevel, right? So what that means is if there is an electron found within a 1S sublevel, it is going to be running around within this space. These sublevels are actually what are called electron probability distributions. And what that means is in this space here, there's a 90% chance the electron is in here. The other 10% is the electron might kind of be venturing kind of like a little bit outside the boundary a little bit, but it'll come back. They're constantly moving. And so 90% chance that they're in that area that we call the 1S subshell. If this were a 2S subshell, then the total volume of area would be larger. And so the 2S subshell would kind of like come out to here. If this were a 3S subshell, then that, of course, would incorporate a larger volume, and so on. You guys get the idea? All S's look like spheres. Okay? All right. What if the electrons are in a p subshell? The p subshells are actually divided into three areas. The first one, which lies along the x-axis, is called a px orbital because it lies along the x-axis. The second one is called a py, and the third one is pz, so xyz plane. Now, even though we're showing you these broken up individually, understand that they all lie over a common origin. So collectively, putting them all together, they're actually all still over one common center point, one common origin. And again, this is probability distribution, so each one of these shapes, which we call dumbbells, there's a 90% chance that the px electrons are in here. Okay. So p orbitals are broken up into three parts. I'm sorry, three p subshells are broken up into three parts. And these parts we call orbitals. If the electron is in the d subshell, the d subshell is divided into 5 orbitals. Now, these start to get a little bit more complicated and a little bit more fragmented. All right, these names you don't need to know. The point is there's 5 separations of the d subshell. Each orbital, each of these 5 orbitals can hold a maximum of 2 electrons.
Quick question, Mr. Park. Mortar and pestle?
Do we have one?
We do. They're in the back on the bottom of the AP prep room.
Awesome, thank you.
So 2 electrons max per orbital. Since there's 5 orbitals, that means the capacity of the d subshell is 10. It doesn't mean that a d subshell has to have 10, it just means the maximum capacity is 10. Likewise with the p's, 2 each, which means 6 is the max capacity. And of course, the s's would be 2. We mentioned F sublevels. Well, there are 7 divisions or 7 orbitals of the F sublevel, and they get even crazier. Now, the reason why these shapes look so weird is because we mentioned earlier how the electron has behaves like a wave. Okay, the electron, because it behaves like a wave, how it travels is not linear. It's not like throwing a baseball where it just travels in a straight line. All right, the wave function actually has to kind of eventually reconnect at the place where it started. And so there's only certain mathematical increments that are allowable for that. And so because of that, the electron will only be allowed to exist within certain increments of this pattern, which means it's only allowable in certain 3D spaces. All right? It's not flying around willy-nilly like a bumblebee. It has a set path that it can actually travel through because that path has to be a multiple of a certain increment. Okay? All right, with that aside, we have these different sublevels, and back to this chart here, you see some arrows on this chart. These arrows are what we call order of fill. And we start here. What the order of fill represents is from lowest energy to highest energy where the sublevels are in relation from the nucleus moving outward. So the 1s is closest to the nucleus. If you read this kind of like a typewriter, and if you come down and you hit the left column, every time you hit the very, very end, you start a new arrow. And so after 1s comes 2s. And after 2s comes 2p, and then 3s. And then after that, 3p, and then 4s. These arrows are shifting a little bit. And then after 4s comes 3. You know, I'm going to redraw these because I think they're kind of skewed. So what I'm saying is, when we count electrons, when we organize our electrons, we have to follow the order of fill, right? Order of fill, this is also known as the Aufbau principle. The fact that you start from smaller electron configurations, and then if you continue to count more electrons, they get bigger and bigger because they just build upon the previous. So, what sublevel follows 4p? 5s, good. What sublevel follows 4s? 3d. And see, this is weird. This is where it gets weird because energy level 4, you'd think, oh, that's a higher energy level, right? But the 4s sublevel, we count those electrons before we count the electrons in the 3d sublevel. And the reason why is kind of complicated, right? But just suffice to say that the 4s sublevel is a lower energy state than the 3d sublevel, like on average. So we filled here first before we fill here. Okay. So we have these energy levels. There's a certain order, and we know that these different types of sublevels have different capacities, right? The S's holds 2 electrons, the P's hold 6, the D's hold 10, F's hold 14. There's no G sublevel shown on here, but if there was, if we did include a G, how many orbitals do you think it would have? It would have 9. And the maximum number of electrons, therefore, would be 18. Okay? Now, it turns out that the G is entirely theoretical. There's no evidence that G exists because if we follow the order of fill, like if I were to finish writing this out, okay, so 7p here, there would be a 6d here, there's a 5f here, there's an 8s here. Imagine that if I just kind of added to this and created a new arrow, there's no element in period 8. Because there's no element in period 8, this diagram terminates here. Because it terminates here, we will never see a G subshell in use because the G subshell would be here. But we can't get there because we don't have anything to put in 8s. Does that make sense? It's hypothetical, right? But it doesn't exist. It's just like we follow a pattern, it exists, but there's no actual element that has it. So that's why this chart ends there. Okay. So this picture here shows us in relation to the nucleus would be at the very bottom of this chart. Moving outward, the first and closest sublevel, like we said before, was 1s, and then 2s, and then 2p, and then 3s, and then 3p. But before we go to 3D, note that the 4s sneaks in underneath. So it actually goes 3s, 3p, 4s, and this follows the fill order. If you follow from bottom to top, it's going to follow the same exact fill order that we just mentioned. And the number of circles, why are there different numbers of circles for each of these sublevels? The different number of orbitals. S's have 1 orbital, P's have 3, D's have 5. F's have 7. The higher the energy level, the more sublevels, and therefore the more complicated it is. Also, the more bleeding there is of one into the next. Right? So the more sublevels you have, the more of this funny business you have with getting out of order, with the 4, then the 5, and so on. All right, that is the theory. What is the practical aspect of this? When we're writing electron configurations, we need to start with just two things. We need to start with the number of electrons that there are. And we need to be able to follow the fill order. So, sodium, 11 electrons. The way we write it is, first we write 1s2. We write 1s first because that is the lowest energy level. We write the 2 because the 2 is the capacity of an s. What comes next after the 1s is 2s. It is still an s. It still has a capacity of 2, so we put the 2 there and we move on. After 2s comes 2p. The capacity of p is 6. After 2p comes 3s. Now the capacity of s is 2, but we only have one more electron to place because we only had 11 at the beginning. So we are done. This is the electron configuration, also called SPDF notation. So, before we move on, we need to make sure that we're able to do this, so let's pick another element. Let's say sulfur. How many electrons does sulfur have? 16. All right, so we go in order. 1s and then a 2. 2s and then a 2. 2p and then a 6. That is 10 electrons so far, and you have to account for all 16, so we keep going. What comes after 2p? 3s. And that has a 2. That is 12 so far. What comes after 3s? 3p. And how many electrons do we have left? 4. So we put a 4 there. Okay, that's our SPDF notation for sulfur. Let's pick another one. Let's do nickel. Nickel has 28 electrons, and these always start the same way. Aufbau principle. Build up from the bottom. Take a second, jot it down, and see what you get. All right, so it would look like this. We end on 3d8. Everybody get that? Okay, and again, this is an example where we have that jumping of numbers, right? After 3p, 4s actually comes before 3d. Okay. So as you can imagine, if I asked you to write the SPDF notation for gold, that would be kind of annoying, right? Because of how many sublevels there are. You could do it, but then there's an alternate method. It's called shorthand. And so shorthand, to find shorthand, this is what you do. Find the noble gas which precedes the element in question. So for gold, what noble gas comes numerically before gold? Xenon. How many electrons does xenon count up through? 54. And so the last question is, for xenon, do you see how xenon is in the p block? Okay, count what row it's in. What period is it in from the top? Is it 1, 2, 3, what? What is it? It's 5. So xenon represents the end of sublevel 5p. And the reason why that's worth noting is because now you know what sublevel comes next in the sequence. According to the chart, what's after 5p? And hint, S's always follow P's. 6S, right. And so you continue on from here. So xenon is 54, plus 2 is 56. What comes after 6S? Careful. Now, this is the first appearance of the F. Here, let's reference that here. 6S. After 6S comes 4F. Okay. So 4F 14. That makes for a total of 70 electrons so far. We have to work our way up to 79. So after 4F comes what? 5D. So a little more thought is involved, but there's definitely less writing. All right, and so when we refer to the larger elements, typically we just write it in shorthand. Okay. How are we doing with SPDF notation? We're doing okay? Okay, so the next natural step, actually, just to make sure, I just want us to do 2 more examples to make sure we're okay with this. So I want you to write out the regular bromine, and then I want you to do shorthand for lead. Okay, so write out SPDF notation for bromine, and then write out the shorthand for lead. All right, somebody read off their bromine SPDF notation for me. Who's got it? Slow down. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Everybody get that? Okay, good. That's correct. Okay, for lead, dealing with shorthand here, let's find lead. Lead is element 82. The element which, the noble gas which precedes it is what? Xenon. And xenon, again, it represents 54 electrons. Lead is 82, so we got to get up to 82. Okay, so what follows xenon? 6s2, and then 4f14, that is now 70 electrons. And then 5d10, that is now 80. 6p2. There you go. Okay, so SPDF notation, regular and shorthand. Are we okay? Yeah? All right. So we've mentioned valence electrons a little bit before, but we haven't really defined them. The valence electrons are the highest energy electrons. These are the electrons that actually interact for bonding purposes, and these are the ones that can be ionized because they are the outermost. They are the ones that are actually exposed, right? Because not all electrons are exposed. Most of the electrons are tucked away underneath. That's what we call the core. They're typically going to be the s and p electrons. So the way that you figure out what the valence electrons are is after you write the SPDF notation, find the highest energy level. So, for example, for silicon, this is the SPDF notation for silicon. What is the highest energy level represented? 1, 2, or 3? 3. Oops. Those are your valence electrons. There's 4 of them. For bromine, so for bromine, which we'll just copy and paste this. What is the highest energy level shown? 4. Here and here. So your valence electrons can be the combination of s and p's, but your valence electrons will never be d's and they'll never be f's because those will never be the highest energy level number. So 7 valence electrons. Okay? The highest number. Weird thing happens. The transition block, the D subshell. Because of the delay when the D subshell fills and because of the proximity to the nucleus, any transition metal will have a default number of valence electrons based on the preceding S. So for vanadium, right? Vanadium is element 23. So let's do shorthand for vanadium. So let's say argon, and then 4s2, 3d, 3. How many valence electrons does it have? 2. Here they are. If I ask you the same question, well, I am asking you the same question for iron and for copper. Iron is 4s2, 3d6. Copper is 4s2, 3d9. You're increasing the electrons in the D subshell, yes, but the 3d subshell is not the highest subshell. The highest subshell is 4s. Therefore, how many valence electrons are in iron? 2. Copper? 2. Nickel? 2. Manganese? Do you get the idea? Okay. What about the 4d subshell? What if I picked silver or palladium or cadmium or molybdenum? Anything in the 4d subshell. How many valence electrons are in those elements? Just 2. By default. Transition metals, D block, same thing with F. By default, 2 valence electrons, which are the s electrons that come right before. Okay? Alrighty. So, from a practical standpoint, SPDF notation, it's a way of counting electrons. It's fine. But what's more useful is a pictorial representation. So we draw what's called orbital diagrams. And because you know that S's have 1 orbital and P's have 3 orbitals and D's have 5 and F's have 7, if we draw out orbital diagrams, this gives us a better picture of what's going on with the electrons and allows us to make better predictions of what's going to happen, how they're going to react, what they're going to do. So in this first example here, oxygen 1s2, 2s2, 2p4. Here's the 1s. It's a circle, and it's got 2 electrons because every orbital holds 2 electrons. Now, in every orbital, your electrons cannot have the same direction of spin. That is why the first one faces up and the second one faces down. You will never have them pointing in the same direction. Okay? That's what we call the Pauli exclusion principle. They must have opposite spin. Okay. So we are still progressing through fill order because we're basing this off of SPDF notation. 1s2, 2s2, 2p. Okay. And then when you get to an orbital like this, when you get to a sublevel like p, 3 circles, there's 4 electrons, so they are inserted as 1, 2, 3, and 4. They are order specific. And the reason why they are order specific is because you cannot bunch up electrons because they're going to repel each other, and if they repel each other, they're going to spread out. Watch. What if I tried to draw my 2p4 electrons this way? Now, what if I did this? There is a third orbital that is vacant. The repulsion taking place between electrons in those orbitals is going to bump one of those electrons out. And that's why, whoops, that's why that one electron is not there. Yeah, Karan.
What determines the spin of the electrons?
It's arbitrary. It's just for balance, for electrostatic balance. If one is spinning in one direction, the other one has to be counter to it. Otherwise, you have a net spin, which is unsustainable.
What is spin of electrons?
So remember how we said that the electron's existence within a sublevel is based on a predetermined mathematical waveform? Okay, so those waveforms must net out at 0. That's why they must be spinning in that. Spin is an oversimplification of what we really mean to be waveform pattern. Okay, just put it that way. Okay, so do you guys get that the electrons actually, they don't bunch up if there's extra space available? Okay, they will settle out and they will all spread out, and they will only stay paired if they have to. This electron here, electron number 4, that has to be paired because there's nowhere else, it doesn't have an orbital of its own. So it's just going to be there. Okay.
Once it gets paired, does it stay there or can it move around? Arbitrary.
So whether it moves around or not doesn't actually matter, because when we visualize the sum of 3p orbitals in 3D space, the one that is vacant is the one that's going to allow for a bond to form, and if the electron has moved from one orbital to another, the same total number of vacancies is still available. So it actually doesn't matter. By convention, we fill them from left to right. Okay. We already talked about the outer shells. So let's just make sure that we can draw a couple of orbital diagrams. So sulfur, 16 electrons. Let's just do shorthand to save time. So we start with neon. Okay, so neon is 2p, so after 2p comes 3s. 2, 3p, 4. That is how the orbital diagram for sulfur would look. Oh, I forgot to highlight this term. Hund's rule. That's what we just described, how electrons will pair. They will not stay paired, they will spread out. Now, a technical definition. I don't know if you'll ever have to answer a question about this, but you should know what it is. The technical definition of Hund's rule. Electrons will have minimum energy when maximum number of half-filled orbitals is achieved. It's kind of a mouthful. Just stop and think about it for a second. Minimum energy is a theme that you're going to start hearing me say over and over again through this unit and especially through next unit. Minimum energy, it means stable. Low energy means stable. Okay? So the electrons will have a minimum energy configuration when there's a maximum number of half-filled orbitals, which means half-filled is preferred over bunched electrons, especially when there's an open orbital. Okay? I mean, it means you always spread them out. That's what it means. Okay. Let's draw the orbital diagram for iron. So iron is 26 electrons. We're going to start with argon. Oops. Argon represents 18 electrons. Since argon is 3p, we begin with 4s. And then after 4s comes 3d. So 4s2, 3d6, so up, 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 up. Last one, down. Yes, you always draw the full set of orbitals regardless if they're filled or not. Yeah. Okay. Are we okay with drawing circles? Orbital diagrams? Okay. So, what is the relevance? What kind of information do we get from drawing orbital diagrams? For one, we see if an element is what we call a paramagnetic. If there are unpaired electrons, it will be influenced by a magnetic field, i.e., it will be magnetic. And it will be more magnetic the more half-filled orbitals there are. So an element with one unpaired electron versus an element with like 5 unpaired electrons, the one with 5 is going to be way more magnetic. Okay? It literally means you can like hold a magnet up to it and you can influence the movement of the element. Diamagnetic, di for 2, diamagnetic. It's unable to be affected by magnets. It has no unpaired electrons. No unpaired electrons. Okay. So when we follow fill order, and you make sure that you go, you finish the 2s before you go to the 2p, and then you finish 2p before you go to 3s, and you finish 3s before you go to 3p, right? The majority of elements follow the fill order. But of course, there are exceptions and some things, there's some bumps in the road, okay? Let me show you a couple of them. There's a lot of them, but I would say that these are really the only 4 you need to know, and it's actually easy because these guys are in some of the same families. All right, so here, watch. For copper, copper is element 29. So we go 4s, 2, 3d, 9. This is what we expect from copper. Does that diagram make sense? Okay. Oddly, here's how copper is actually configured. What happened? There's S electron has moved into the D subshell. And this is how it's actually observed. Okay, now, how can this happen? Well, if we go and examine closely the relative proximity of the 3D and 4S, look at this line right here. This line is 3D. Here's 4S. Look how close they are to each other. So even though 4S is lower in energy, and we fill 4S first before 3D, when we get into the weeds, we get into these higher levels, there's some wonky stuff going on with electron fill order. And it turns out that there's particular places where we notice it. So copper does this, but you know who else does this? Silver and gold. What do silver and gold have in common with copper? Same family. Same family. So silver, if we do the shorthand for silver, let's start with Kr. So after Kr, so let's see, 1, 2, 3, 4, so 5. So 5s2, 4d9. We expect silver to behave like this. But what we observe is this. Did the exact same thing that copper did. It pulled the S2 electron into the D10 position. And gold does the same thing. So, this happens naturally. If it happens naturally, that means this must be the lower energy configuration. And it's weird and it's counter to the Aufbau, but it happens and it's observed. So we can say then in the D9 family, everybody see what I mean by that? D9, the 9th column of the D block, this kind of thing happens. The other place where it happens is the D4 family. Question, Nate?
How would this affect valence electrons?
So it affects it because now effectively it would appear that your default number of valence electrons for the D9 family elements would be 1, which explains why silver's charge is predominantly +1 and gold's charge is predominantly +1. Copper is +1 or +2. Okay, so but I'm showing this to you. These are examples that happen, but there's never going to be a really big question about these. Okay, these we're trying to move away from nitpicking specific exceptions. I'm just showing these to you so you understand, because you're going to still come across some literature that refers to this. Okay, let's just do the chromium, and then I think we'll be done with this. So chromium is 24. So we're going to start with argon. So 4s2, 3d4. This is what we expect from chromium. Okay, you guys, that makes sense? But here's what happens. Did the same thing. It pulled the s electron into the last d orbital. Molybdenum does this also. MO. So D4, D9. Family D4, family D9. They pull that second s electron into the last d orbital. Okay. There are other exceptions we're not going to touch, because there's kind of no need to get that deep, right? But weird things happen, especially when sublevels are really close to each other energy-wise. All right. How are we doing, guys? Let's take a break.